Hello everyone, I welcome you all to the session Design for Test. The intention of this session is to have an overview on Design for Test, which is part of VLSI industry. Now let's begin. Yeah, the intended audience for this course would be any BTech and MTech graduates who are in their final year or those who have recently passed out, specifically with electronics background, can attend this course. It's not specifically electronics, but who are interested in electronics, who wanted to build their career in electronics field, can also attend this course. And also the engineers who are really passionate to switch their careers into VLSI domain. They have already worked in some other domain and they wanted to understand more on VLSI and they wanted to switch into VLSI domain, can also opt for this course. And also the college lecturers. All of them can get benefited by gaining simultaneous hands-on industrial experience on a real-time chip making process. Okay. Moving on to the next slide. On this slide, I have mentioned the prerequisite skills for this DFT course. These are very basic and good to have skills. If not, you can spare just few days to work on it. That's not an issue. It's not mandatory that you should have these skills, but you can spare few days to build on these skills. So first of all, you must have a basic understanding of digital electronics. And then you should be very comfortable to work on EDA tools. As a DFT engineer, you'll be working more on the EDA tools, that is the electronic design automation tools. So you should be comfortable to work on those tools. Then, as you know that DFT is part of a VLSI domain, a DFT engineer will be working with other engineers from physical design, static timing analysis, and many other teams. All these teams work together in the entire chip designing process. So it is good to have a sound knowledge on the entire VLSI design flow. And also it's desirable to have other skills like Unix and Linux and like scripting languages like Perl, Python, TCL. All these will be really helpful while working on the industry. So these are the skills that it's good for you to build up during this course. So now let's move on to the next slide. Yeah. So this is the outline of my overall session. I'll start introducing to the VLSI industry and also on the importance of DFT and why do we need DFT, with little bit insights on the design flow and the DFT flow. And then I'll be moving on to giving you a glimpse on the steps in a specific DFT flow, as well as we will discuss in detail on a case study of a live issue. So I'll discuss a live issue, how it is seen in industry and how do we work on it, how do we resolve on it. So I'll be detail that in the next coming session. And finally, I'll be walking you through the role of a DFT engineer and the opportunities for DFT engineers in semiconductor industry by showing you the overall structure of this upcoming sessions also. So now let's begin with the VLSI industry. So as you see from the picture that VLSI industry is categorized into three major fields. It starts with the system on chip design where EDA tools, that's the design automation tools, are utilized in the chip designing process. So a DFT engineer will be working under this field. Yeah. So once the design is over, these system on chips are manufactured. That is a field which needs entirely different experience. So you shouldn't confuse with the DFT engineer works in the manufacturing as well as testing. These are entirely three different fields. And a DFT engineer totally works in the design area with the EDA tools that you have to understand. So, and once the chips are designed and then these are manufactured. And once these chips are manufactured, it has to be tested with a predefined test patterns. So that is done using an automatic test equipment. I'll be showing a little bit of it in the coming slides. So we'll go about in details in the coming slides. So here I'll be discussing a typical system on chip design. So you can see in the slide, this is a picture of a typical system on chip. So you can start looking from the leftmost side. So this system on chip is categorized into different blocks with IP libraries. So the system on chip is designed like as you saw in this slide. The entire chip will be there. So the entire chip is being tested using a tester. So the picture shows a VeriG tester. And in this tester, the entire system on chips are tested. So to test these chips, we need some patterns. That is the inputs. So these inputs are provided by a DFT engineer. And in the tester, these inputs are provided and these patterns are tested. Once we get the patterns, this is being verified with the expected patterns. So if there is a variation in that, we say that there is an issue. That particular system on chip doesn't pass. So this is just an overall view. So I'll just give an view on the different manufacturing defects, some of the manufacturing defects that are usually seen. You don't need to go in depth to understand these. It's just an overview for you to get an understanding of what it is in industry. So as you know that in system on chip design, there are billions of transistors are integrated in a single piece of silicon. As it is going smaller and smaller, it's prone to more and more issues. Issues, we call it as over here, defects or as a fault. So these are some of the defects that is coming like in what we get in industry. So as a DFT engineer, we don't go in depth into it, but we do it in a logically. That is like we model it as a fault and we work on those. So here in this slide, I'm showing you the need for DFT and the importance of it. So the DFT, it's a technique actually. It's a technique that helps us to make the chip testable once it is produced. And also it helps us to detect defects in a design at a pre-production stage. And also this DFT help us to identify the design if it is a faulty or free of any fault. This in turn will help us to reduce the test time and like the better quality chips are being produced. So you will understand more about it in detail in the coming slides. It's just an idea to give, the intention of this is just to give an overall view of what happens in DFT. So this is something you need to stay focused on this slide. So this is a system on chip design flow. So we won't be working on the entire flow. We will be working on the part of it. You can see a DFT team, which I have mentioned in the picture. So we will be working as a DFT engineer over here. But this is the entire flow. But I'll explain to you what this flow has. So this is a typical system on chip design flow. And each company follows their own specific flow. You may be familiar with this flow, but let me walk you through it once again. So first is a design specification. When we design some chip, we need to first of all understand its specific application that we are targeting on. For example, we are targeting a Bluetooth or Ethernet or a memories, something we are targeting on. So we have to understand its specification first of all. So it will be decided by the company before the actual design process starts. And there is a separate team called the RTL team. That's the RTL engineers who write the code for the design according to the design specification. So once we get the specification, we write the code for the design. So they write the code in VHDL or Verilog, etc., based on the design necessity. So once the design is done, verification engineers has to functionally verify it. So that comes the design entry. So the design entry is written in the hardware description language or Verilog or system Verilog. All different languages are used for entering the design. So once the design is entered, then another team called the functional verification team verifies the functionality of the design, whether it is like functionally working or not. So that is done by the verification engineers. So then after that, the next team, that is a synthesis team, comes into picture. So in synthesis, the actual implementation of the logic gates are done. That is, the Verilog code of a design is converted into a structural form. Basically, you can see here how the logic gates are connected. So in synthesis, the logic gates comes into picture. The design specification is like whatever the idea or the specification is there, you convert that into a VHDL or a code, RTL form. So once that RTL form is done, you have to make that to a gate level design. So where the circuit comes into picture. So once these circuit is coming into picture, then the role of a DFT engineer comes into picture. That is, the DFT is implemented. So over there is one more team called the physical design team who works on the actual layout of the chip. So their work is to design the layout of the chip, and we won't go in depth in understanding these areas as our primary focus is on DFT. Okay, so once the design for test is implemented on a system on chip, we generate patterns using a method called automatic test pattern generation. It's a technique where which I'll detail in the coming slides. And once the patterns are generated, this has to be validated. So we use the gate level simulation to validate these patterns before sending it to the tape out. So the tape out is the actual manufacturer of the chip. Okay, so you will understand it further in the coming slides. So let's move on to the next slide, that is the DFT flow. Okay, in this slide, I'll be discussing about a typical DFT flow. Every company follows their own specific flow. Yeah, this is just an example flow that starts with a gate level netlist, and the other flows, there are different possible ways, and every company follows in their own way. So to illustrate this DFT flow, we will walk through a design example of a system on chip design that is mostly digital logic and has variety of memories spread across the design. So here the flow starts the first with a scan insertion. So please look at the highlighted number 1 marking in the picture. So in the picture, it's a system on chip. In that, you please look on the highlighted mark 1. So here the first step, that is a scan insertion step, is done. So scan insertion is a process of inserting the test structures into the design. This will actually help us to control and observe the faults at the output. So moving forward, I'll explain to you what these faults are in a circuit. So you just need to understand here is that you have a system on chip. Inside that, you are inserting some test structures that will help us to test these system on chips. So so the scan insertion is a DFT technique for increasing the testability of a design. So once the design is ready, it needs to be tested. This scan structure enables us to test the design. So it is basically a serial connection of storage elements in the design stitched into a scan register, which is the scan chains. So like this will be like elaborated in the coming sessions, but here I'm just giving you an overall idea of what it is. Okay, so then it comes after this, the next step is the compression. So please look at the highlighted number 2 marking in the picture. So which has a decompressor and a compressor over here. In this technique, the compression allows us to compress the test patterns. So the chip is huge, and there is a need for so many like test patterns. So the test patterns, when you start testing, it will take a huge amount of time, like days, months. So that is not possible, because like we need the chips ready like in the market. Otherwise, like it's difficult. Like the chips has to be ready within 1 or 2 months. So there is another technique, that is the compression logic. So what we do is that we implement a decompressor and a compressor over here that will actually help us to reduce the size of the test pattern, and this will in turn reduce the overall testing time. Okay, so after compression, the embed is inserted. Please look at the highlighted number 3 marking in the picture. Okay, this technique is used to generate a built-in self-test controllers and memory blocks. You might be knowing about the importance of a memory blocks in a design, right? So this is similar to that, but this is a built-in self-test mode over here. So this will help us to implement memories over here. Then after this, the next step is to insert the boundary scan insertion. So you can see the tab part in the highlighted area number 4. So what it actually does is that it is like, you might have been heard of JTAG, right? So it's an IEEE standard structure that can drive all the MBIS controllers and all the core logic, which scan chains are inserted in the design through a test access port. So using this test access port, what you see in the picture, right? The chip gets accessed. The inside of the chip has to be accessed. So the patterns are fed through this tap controllers, and through tap controllers, it goes through the boundary of the chip, and through the boundary, it goes to the decompressor. Through the decompressor, the compressed pattern goes inside the scan chains. So using the scan chains, we get access to the logic gates or the logic circuitry inside the chip. So once these are done, then we implement ATPG. As I told you, like ATPG is a technique of automatic test pattern generation. So we have to test this chip using some patterns. So you can see the highlighted phi in this. So in this, like some input values, that's ones and zeros, are given to the core design, and the simulated results are observed at the output. So these are given to the circuit, they are being simulated, and whatever the result we got, we fetch it back towards the output. And this process happens in the ATE equipment, as I've shown you earlier. So over there, they just test it, they just check it whether the expected output matches with the real output. So we have given them some patterns, and it is being tested on the chip, and whatever the expected outputs are there, right, that are being tested to see whether it matches or it has a difference or some issues. So once this is done, the ATPG test patterns are verified, and then these results go to the tester, and the tester verifies whether it matches with the expected result or not. So they all in turn help us to find where in the device these potential defects are located. This process is called scan-based diagnostics. That is the final step. So as you see, first is scan insertion happens, then a compression logic is there. After that, we insert a memory BIST. Then over that, a boundary scan is also inserted. Once this insertion happens, then the pattern generation happens. That is the ATPG. So once this pattern generation happens, we send it to the tester. So the tester tests that in an equipment with these patterns. So they finally come up with the result saying that these patterns are matching, these patterns are having some issues. So as a DFT engineer, we see that, okay, there is some issue. So we need to sit and debug that. So we work on the debug of those issues. So that comes as a diagnostic part. So moving on to the next slide. Yeah, so this I have already explained. Like, so these are like the basic things, that is the scan insertion. So what a scan insertion is, it's a serial connection of storage elements, that is a scan cells in the design that are stitched together into scan registers. And to the scan register, we are feeding some input values. These input values are, like as you see in this picture, these input values are fed to the core logic, and these are being taken out. So once these are taken out, we just test it in the tester. So that is the importance of inserting scan chains. The thing is that if it is a bigger design, means we can test it using some equipments. As the design is and the technology scaling is happening, and it's now people are working on 10 nanometer technology and even lower than that. So in that, it's really very difficult to test the circuits in that. So we do scan chain insertion. So the scan chain insertion actually help us to give some patterns to that, test it, and then do see that, okay, there can be a chance of potential defects in this particular part. So that is how they concluded.